Let's start from the very beginning, the idea of motion and force. In daily life, you notice, a football doesn't move unless you kick it. A bicycle slows down when you stop pedaling. A box doesn't move unless pushed. This creates a natural belief. Objects need force to move. But here's the twist. This idea is partially wrong. Scientists asked, does motion always need a force, or does force only change motion? This question led to the development of laws of motion. Ancient philosopher Aristotle believed a force is required to keep an object moving. Example, arrow keeps moving because air pushes it. Cart moves only if continuously pulled. This matched everyday experience, so people believed it for nearly 2,000 years. Why does a rolling ball stop? Not because force disappears, but because of friction, opposing force. So actually, force is needed to overcome friction, not to maintain motion. Galileo changed everything. He imagined, what if there was no friction? He experimented with inclined planes and concluded, objects moving downhill accelerate, objects moving uphill slow down. Objects on flat surface should move forever if no friction. Galileo discovered a body in motion does not need force to keep moving. Instead, it keeps moving naturally unless something stops it. In real life, friction always exists. Air resistance always acts. So motion eventually stops. But in an ideal frictionless world, motion would continue forever. Galileo proved that these two are equivalent, rest and uniform motion, constant speed in straight line. Both happen when no net force acts. This led to the concept of inertia equals resistance to change. Object at rest stays at rest. Object in motion keeps moving, unless an external force acts. This idea destroyed old thinking and became the foundation of physics. It helped explain why passengers jerk in buses, why objects resist motion, and why motion doesn't need continuous force. Force is not required to maintain motion. Force is required to change motion. Friction created confusion historically. Galileo introduced inertia. Motion without force is possible in the ideal case. Now we deal directly on what we learned from Galileo. Isaac Newton converted Galileo's ideas into a clear law. A body remains at rest or in uniform straight-line motion unless acted upon by an external force. This law says no force means no change in motion. Force leads to a change in motion, either in speed or in direction. So, force is not needed to keep an object moving. Force is needed to change motion. Case 1. Object at rest. A book on a table remains at rest. Why? No net force acts. Even though forces exist, gravity pulls down and the table pushes up. These cancel out so that the net force is zero. Case 2. Object in motion. A car moving at constant speed or a spaceship drifting in space will continue in motion in a straight line if no net force acts on it. Its motion persists forever without outside influences. Newton's first law can be written mathematically as if net force equals zero, then acceleration is zero. F net equals zero implies that acceleration A equals zero. This means velocity remains constant and there's no change in speed or direction. Inertia is resistance to change in motion. There are three types. 1. Inertia of rest. An object resists moving, like a heavy box hard to push. 2. Inertia of motion. A moving object resists stopping. 3. Inertia of direction. Object resists changing direction. More mass means more inertia. For example, a truck is harder to push than a bicycle, and a stone is harder to start moving than a small ball. So, mass is a measure of inertia. Bigger mass equals greater resistance to change. Real-life example 1. Bus starts suddenly. Your feet move with the bus due to friction, but your upper body stays at rest due to inertia. This makes you fall backward when the bus moves suddenly. Real-life example 2. Bus stops suddenly. Your feet stop when the bus halts, but your body keeps moving forward due to inertia. You end up falling forward inside the bus. Example 3. Kicking a ball. The ball only moves when a force or kick is applied. It eventually stops due to friction with the ground. No force means no motion starts, and friction eventually ends it. Example 4. Coin trick. When a card is flicked away from below a coin, the coin falls straight down. This demonstrates the inertia of rest as the coin resists moving until gravity pulls it down. Balanced forces. Equal and opposite forces acting on an object create no change in motion. For example, a book resting stably on a table. Unbalanced forces, not equal, cause motion or acceleration, like pushing a box hard enough that it starts to move. Important concept: net force. Even if many forces act, only the net resultant force matters. If net force is 0, there's no change. If net force is not 0, the object's motion will change, speed up, slow down, or turn. Newton's first law is powerful. It defines force properly, introduces the concept of inertia, explains everyday examples of motion, and forms the foundation for Newton's second and third laws. Inst-doodle summary. Objects don't need force to move, they need force to change motion. Inertia resists any change in motion. Mass measures inertia. Net force is what decides how an object's motion changes. Part 3. Newton's second law, force, momentum, and deep understanding. Now we move to the most important and powerful law in mechanics. 1. Why do we need second law? First law tells us when force equals 0, no change in motion. But what if force is not equal to 0? We need a rule to answer. How much acceleration? How does force affect motion? That's where second law comes in. 2. Newton's second law statement. The rate of change of momentum of a body is directly proportional to the applied force and occurs in the direction of the force. What is momentum? Momentum is a key concept. Momentum equals mass times velocity. Symbol P. It is a vector, has direction. Intuition. Heavy object, more momentum. Fast object, more momentum. Examples: truck, bicycle. Bullet, fast. Stone, slow. 4. Core idea of second law. Force depends on how quickly momentum changes. Faster change, bigger force. Slower change, smaller force. 5. Mathematical form. From definition, force equals rate of change of momentum. F equals dp divided by dt. When mass is constant, since P equals mv, then F equals ma. 7. Meaning of F equals ma. This equation tells more force, more acceleration. More mass, less acceleration. Example: push empty cart, moves easily. Push loaded truck, hard to move. Same force, different acceleration. 8. Direction of force. Force and acceleration are always in the same direction. Example: push forward, object accelerates forward. Push backward, slows down. 9. Real-life applications. Catching a ball. Cricketer moves hands backward, increases time to stop ball, reduces force, less injury. Bullet impact. High speed, large momentum, stops quickly, huge force, causes damage. Braking car. Car slows due to force opposite motion. Faster stop, larger force. 10. Impulse concept. Sometimes force acts for very short time. Impulse equals force times time. Impulse equals F delta T equals delta P. Meaning, impulse equals change in momentum. Examples: bat hitting ball, hammer hitting nail, airbags in cars, increase time, reduce force, safer. Instoodle summary. Force changes momentum. Momentum equals mass times velocity. F equals dp dt, general law. F equals ma, simplified law. More mass, less acceleration. Impulse explains short-time forces. Art 4. Newton's third law, action, reaction, and deep intuition. Now we move to one of the most famous and often misunderstood scientific laws. Newton's third law statement: for every action there is an equal and opposite reaction. Whenever two objects interact, they both apply forces on each other that are equal in magnitude and opposite in direction. Mathematical form: F of AB equals negative F of BA, meaning the force on object A by B is the opposite of the force on B by A. Key insight: forces always come in pairs. You cannot have a single force or a one-sided interaction. Common misconception: people think action happens first and reaction happens later. This is wrong. The truth is, both forces act simultaneously. Another big confusion: people say forces cancel each other. This is incorrect. They act on different bodies, so they do not cancel out. Example: you push a wall. The wall pushes you back. You feel resistance. Your force acts on the wall, and the wall's force acts on you. Real-life examples: walking. You push the ground backward. The ground pushes you forward. That's why you move. Rocket motion. The rocket pushes gases backward, and gases push the rocket forward. This explains motion in space where no air is needed. Gun recoil. Bullet moves forward, and the gun moves backward. The forces are equal and opposite. Swimming. The swimmer pushes water backward, and the water pushes the swimmer forward. Contact versus non-contact forces. The third law applies to both. Contact forces include push, friction, and tension. Non-contact forces include gravity and magnetic force. Example: the Earth pulls the apple down, and the apple pulls the Earth up. However, the effect on the Earth is very small due to its huge mass. Why effects look different? Forces are equal, but effects differ because acceleration equals force divided by mass. A small mass gives large acceleration. A large mass gives small acceleration. Deep concept: internal versus external forces. Internal forces, action-reaction inside a system, cancel each other. External forces affect motion of the system. This leads to conservation of momentum. Forces always occur in pairs. They are equal and opposite, act on different bodies, do not cancel each other, and are responsible for motion like walking, rockets, and recoil. Part 5. Conservation of momentum. Deep intuition plus collisions. Now we connect second law plus third law to get one of the most powerful principles in physics. What is conservation of momentum? In an isolated system, no external force, total momentum always remains constant. 2. Mathematical statement: P initial equals P final. Or for two bodies, m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. 3. What is an isolated system? A system where no external force acts. Examples: two objects colliding in space, gun and bullet system, skaters pushing each other. 4. Core idea, very important. Momentum is transferred, not lost. One object loses, another gains. Total remains constant. 5. How it comes from Newton's laws. Step 1. From second law, force equals change in momentum. Step 2. From third law, forces between two bodies are equal and opposite, so momentum changes cancel each other. Result: total momentum remains constant. 6. Real-life examples. Gun and bullet, initially both at rest. Total momentum equals 0. After firing, bullet, forward momentum, gun, backward momentum. Total still equals 0. Two skaters push each other, both move in opposite directions. Momentum conserved. Collision of balls. One ball hits another. Momentum transfers. First slows, second moves. 7. Types of collisions. Elastic collision. Momentum conserved. Kinetic energy also conserved. Example, billiard balls. Inelastic collision, momentum conserved, energy not conserved. Example, clay sticking together. 8. Important insight. Even when objects stick together, energy is lost, momentum is still conserved. 9. Why this law is powerful. It helps us solve collision problems, understand explosions, explain recoil motion, analyze particle physics. 10. Deep intuition trick. Think of momentum like money transfer. One loses 100 rupees, other gains 100 rupees, total money same. In Stoodle's summary, momentum never disappears, only transfers between objects, works only if no external force, comes from second and third law, applies to collisions, explosions, recoil. Part 6. Equilibrium of a particle, force balance, FBD. Now we move to a very practical and problem-solving topic. What is equilibrium? A particle is in equilibrium when the net external force acting on it is zero. 2. Mathematical condition, sum F equals 0. This means all forces cancel each other, no acceleration. 3. Types of equilibrium. Static equilibrium, object at rest. Example, book on table. Dynamic equilibrium, object moving with constant velocity. Example, car moving at constant speed. 4. Breaking forces into components. In real problems, forces act in different directions. So we resolve into horizontal, x direction, vertical, y direction, conditions, sum fx equals 0, sum fy equals 0. 5. What is a free body diagram, FBD? A diagram showing all forces acting on a body. Steps to draw FBD. 1. Isolate the object. 2. Draw all forces acting on it. 3. Label directions. 4. Resolve forces if needed. 6. Common forces in mechanics. Weight, W. Downward force due to gravity, W equals mg. Normal reaction, N. Perpendicular to surface. Tension, T. Force in string rope. Friction, F. Opposes motion. 7. Example, book on table. Forces, weight downward, normal force, upward. Since book is at rest, N equals W, net force equals 0. 8. Example, hanging object. Forces, tension upward, weight downward. Equilibrium condition, T equals mg. 3. Force equilibrium. If three forces act, they form a closed triangle, meaning F1 plus F2 plus F3 equals 0. 10. Why this topic is important. Equilibrium helps in solving mechanics problems, understanding structures, bridges, buildings, analyzing forces clearly. Summary. Equilibrium. Net force equals 0. No acceleration. Resolve forces into components. Use FBD for clarity. Forces balance perfectly. Now we go deeper into the actual forces you'll use in problems and real life. Until now, we said force in general. But in reality, forces come in different types. Contact forces and non-contact forces. Understanding them helps in solving real problems. Contact forces require physical touch, friction, normal force, tension, and spring force. Non-contact forces act from a distance, gravitational force, magnetic force, and electric force. Friction is one of the most important forces. What is friction? It's a force that opposes motion between surfaces in contact. It exists because surfaces are not perfectly smooth and have microscopic roughness. There are two types of friction. Static friction, which prevents motion and acts when an object is at rest, and kinetic friction, which acts when the object is moving. A key property of friction, F is equal to mu n. Here, mu is the coefficient of friction and n is the normal force. Friction adjusts itself up to a limit, and once the limit is exceeded, the object starts moving. Examples of friction in daily life include pushing a heavy box, walking where friction helps movement, and the brakes in vehicles which use friction to stop. What is tension? Tension is the force transmitted through a string, rope, or cable. It always pulls, never pushes. Tension is the same throughout a light string and always acts along the string. Examples of tension include a hanging object suspended from a string and a tug-of-war where both teams pull on a rope. Tension acts along the rope in both cases. When a spring is stretched or compressed, it tries to return to its original shape. This is known as spring force. The more you stretch or compress the spring, the greater the restoring force. Oak's law states that F equals negative kx, where k is the spring constant and x is the displacement. The negative sign indicates the force is in the opposite direction of displacement. What is normal force? Normal force is the force exerted by a surface perpendicular to it. For example, a table supports a book, or the ground supports a person standing. Gravitational force is the force of attraction between masses. Near Earth, the formula is F equals mg. Gravity always acts vertically downward, pulling objects toward Earth's center. Air resistance, or drag, opposes motion in fluids like air or water. It increases with speed. For example, a falling feather faces more air resistance per mass than a stone, so it falls slower. An important insight: most forces we see in daily life, such as friction, normal force, and tension, actually come from electrical forces at the microscopic level. Why do these forces matter? They are used in every physics problem, engineering applications, and in daily life activities, making them essential for understanding how the world works. In summary, forces are of different types. Friction opposes motion, tension pulls through strings and ropes, spring force restores shape, normal force supports objects, and gravity pulls everything down. Now we go deep into friction, one of the most important and tricky topics. Friction is a force that opposes relative motion between two surfaces in contact. It acts parallel to the surface and opposes the motion or the tendency of motion. Friction is both useful and harmful. It is useful for walking as it provides grip with the ground, helps in braking vehicles, and allows writing on paper. However, it also causes wear and tear, produces heat, and reduces the efficiency of machines and devices. There are different types of friction. Static friction acts before motion starts and adjusts according to the applied force, increasing until it reaches a maximum value. Limiting friction, or maximum static friction, is the highest value static friction can reach before movement begins. Limiting friction is the maximum value of static friction and can be represented by the formula F max equals mu Sn, where mu s is the coefficient of static friction. Motion can only start when the applied force becomes greater than the limiting friction. Kinetic friction acts when the object is already moving. It is calculated as Fk equals mu Kn. Importantly, kinetic friction is always less than limiting friction. That's why it is harder to start the motion than to continue it once the object is moving. The laws of friction include: Law 1. Friction is proportional to the normal force. Law 2. Friction is approximately independent of the contact area. Law 3. Friction depends on the nature or roughness of the surfaces in contact. The angle of friction is defined as the angle between the normal force and the resultant force. The formula is tan theta equals mu. A higher value of mu indicates a larger angle. This means a rough surface will produce a larger angle of friction The angle of repose is the angle at which an object just starts to slide down an incline. A key relation in physics is that the angle of repose equals the angle of friction. This connects sliding conditions to frictional characteristics. For a block placed on an inclined plane, the weight acts downward, the normal force acts perpendicular to the surface, and friction acts along the surface. The condition for sliding is if the downhill force exceeds friction, the object will begin to slide. Friction has important real-life applications. In vehicle braking systems, friction between brake pads and wheels stops cars. For climbing, shoes increase friction for better grip. On the road, tires with grooves increase friction for improved control and safety. Ways to reduce unwanted friction include using lubricants such as oil or grease, polishing surfaces to make them smoother, and using ball bearings to minimize contact between moving parts in machines and vehicles. Friction can be increased by making surfaces rougher, adding patterns such as on tires or shoes, or by increasing the normal force pressing surfaces together. These methods improve grip and prevent slipping in practical situations. To summarize, static friction adjusts to applied force up to its limit. Limiting friction is the maximum static friction. Kinetic friction acts during motion. The coefficient mu determines friction strength. Angle of friction is tan-1 mu. Friction is both useful and harmful in various situations. Part 9. Circular motion plus centripetal force core concept. Now we enter a very important and slightly tricky topic, motion in a circle. What is circular motion? It is the motion of an object along a circular path. Examples include a stone tied to a string and rotated, a car turning on a curved road, and planets revolving around the sun. Key observation: even if the speed remains constant in a circular motion, velocity is still changing because the direction of the object is constantly changing as it moves along the path. Remember, velocity refers to both speed and direction. Since direction keeps changing in circular motion, velocity keeps changing too. So acceleration exists even if the speed does not change. Direction of acceleration. In circular motion, acceleration always points towards the center of the circle. This is known as centripetal acceleration. Formula of centripetal acceleration. AC equals v squared over r, where v stands for speed and r stands for the radius of the circle. Centripetal force. From Newton's second law, force equals mass times acceleration. For circular motion, the formula becomes Fc equals mv squared over r. The meaning of centripetal force: it is the force required to keep an object moving in a circle. Without it, the object moves in a straight line due to inertia. Who provides centripetal force? It depends on the situation. String tension for a rotating stone, friction for a car turning on the road, gravity for planets orbiting the sun, and normal force for a roller coaster. Real-life example: a stone in circular motion is pulled inward by the string. The string provides the centripetal force required to keep it moving in a circle. Another example: when a car takes a turn, friction between the tires and the road provides the centripetal force and prevents the car from slipping outwards. In planetary motion, the gravitational force acts as the centripetal force that keeps planets orbiting around the sun in circular or elliptical paths. For a roller coaster, the track pushes inward on the car with a force called normal force. This normal force provides the required centripetal force for circular motion. What happens if there's no centripetal force? The object flies off in a straight line instantly. This behavior is known as tangential motion. An important misconception: many believe there is an outward force called centrifugal force. The truth is that in an inertial frame, only centripetal force exists. The outward feeling is actually due to inertia. Summary: Circular motion means constant speed but changing direction. Acceleration always points towards the center. Centripetal force keeps an object in the circle, provided by tension, friction, gravity, and other forces. Without this force, objects move in a straight line. Institutional Style Explanation Part 10. Problem-solving strategy plus master tips. Final part. Now we bring everything together. This part will teach you how to actually solve numericals like a pro. The biggest mistake students make: they memorize formulas, don't understand concepts, and apply wrong equations. Result: confusion and wrong answers. Golden rule of mechanics: always think in terms of forces. Ask, what forces are acting? In which direction? Is net force zero or not? Step-by-step problem strategy. Step 1. Understand the situation. Is the object at rest or moving? Is velocity constant or is it accelerating? Step 2. Draw free body diagram. FBD. This is the most important step. Include weights mg, normal force n, friction F, tension T. Step 3. Choose axes. Horizontal x-axis, vertical y-axis. For inclined planes, parallel to plane, perpendicular to plane. Step 4. Apply laws. Case 1. Equilibrium. Net force equals 0. Sum F equals 0. Case 2. Motion. Use Newton's second law. F equals ma. Handling friction problems. First, assume static friction. Check if motion starts. If force is greater than limiting friction, use kinetic friction. Handling circular motion. Always identify the source of centripetal force. Apply the formula mv²/r. Handling momentum problems. Check if the system is isolated. If yes, initial momentum equals final momentum. Units and direction very important. Force is measured in newtons, momentum in kilograms per second. Always consider direction because signs matter. Common tricks for exams. Trick 1. If acceleration is 0, forces are balanced. Trick 2. If velocity is constant, net force equals 0. Trick 3. Heavier object means more inertia. Trick 4. Shorter stopping time leads to larger force. Most important concepts to master. Inertia, F equals ma, momentum, friction, circular motion, free body diagram. Final mindset. Think like this. Physics is not formulas. Physics equals understanding forces and motion. Final summary. Start with FBD. Identify forces, apply correct law, solve step by step. Focus on concepts, not memorization.